Hello, today we'll be presenting Model 1 of our roller coaster project. In our project, we have our parts: the hills, the curves, the funnel, and the catcher. In our roller coaster, we chose to start with a steep hill, which is where there's the most gravitational potential energy. We chose to begin with this so that the marble goes down the hill. It has enough kinetic energy to curve and go up and down the hill. We also chose to end with the funnel so it can slow down and the kinetic energy of the marble, and so it can land safely in the catcher. The energy transformations that occur from the start is when it begins at the starting point. It has the most potential energy. As the marble moves down the steep hill, it transforms from gravitational potential energy to kinetic energy and curves. As the marble moves up the hill, the kinetic energy begins decreasing, while the gravitational potential energy increases. While it moves down the hill, the gravitational potential energy decreases as the kinetic energy increases, so that the marble can have enough energy to go through the curve and to the funnel, so it can land safely in the catcher. The law of conservation of energy states that energy cannot be created or destroyed. It can only change form. This applies to our roller coaster because as the marble moves through the track, the gravitational potential energy changes to kinetic energy and some thermal energy, but the total amount of energy of the system stays the same. One force that causes the marble to slow down is friction. Some sources of this force is the air resistance and the friction of the ramp. However, the force that causes the marble to stop is the force of the walls of the catcher. Hello, today we'll be presenting the changed version of our roller coaster lap. In this new model, in order to increase the speed of the marble, we adjusted some parts of the coaster. This includes making the first support taller, increasing the amount of gravitational potential energy, as well as making the third support shorter, to create a more inclined hill to increase the speed of the marble. We also added a wall to the funnel in order to slow down the marble's speed. Finally, we added extra supports to the funnel in order to make it more stable.
Length of the track for Model 1, 128 centimeters. Table 1, Model 1 data. Trial 1, time 2.18 seconds. Trial 2, time 2.68 seconds. Trial 3, time 2.55 seconds. Average time was 2.47 seconds. The formula to calculate speed was speed equals distance over average time. This means speed equals 128 centimeters over 2.47 seconds. This converts to 128 divided by 2.47, which equals 51.8. This is because we rounded it to 3 significant digits. This means our average speed of Model 1 was 51.8 centimeters per second. Length of track for Model 2, 126 centimeters. Table 2, Model 2 data. Trial 1, time 2.13 seconds. Trial 2, time 1.53 seconds. Trial 3, time 2.19 seconds. The average time was 1.95 seconds. In order to calculate speed, You have to divide distance by average time. This means speed equals 126 centimeters over 1.95 seconds. This converts into 126 divided by 1.95. This equals 64.6, which rounded by 3 significant digits gives us our average speed of Model 2, which would be 64.6 centimeters per second. Model 2 had the fastest speed by 12.8 centimeters per second. This is your graph. The scale factor for our scale drawing is 1/2, also known as 1:2. This means that 1 centimeter in the scale drawing represents 2 centimeters on the actual roller coaster.